do it. Who wants to start? All right, I guess we're done then. Yes.
What is azimuth?
Azimuth.
Yeah.
Yes, what is
Is that one of the
azimuth?
tests? I feel like I've never seen that.
What is azimuth? It's on the celestial globes. Let me just go grab it to show you what azimuth is. So azimuth is a way to exactly specify direction along the horizon. So the idea is that due north is called 0 azimuth, and then azimuth increases as you go east. So due north is 0 degrees, due east is 90 degrees, due south is 180 degrees, due west is 270 degrees. So, you know, you might say, it's in the southeast somewhere. With azimuth, you can be more precise. If I wanted to, let's say that this is due north right there, and I was pointing to a star, that like sprinkler right there is a star. I drop down to the horizon, and I say, what's the angle from north? And let's say it might be like 110 degrees or something like that. It's a way to precisely specify direction along the ground. Airplane runways actually are named after the azimuth. If you're landing on runway 22, what that means is you're flying toward azimuth 220 degrees as you land. You take the azimuth divided by 10, that's the name of the runway. Turns out. Fun fact. Okay. Any more questions about that? Okay. So next question then. I'm gonna get this ready where I can start opening files, because I'm sure I'm about to do that. 2019 spring, shared with students. Okay, next question, yes?
Can you go over the line of nodes?
The line of nodes, sure. So here we're talking about, like as it relates to eclipses, the line of nodes for the moon's orbit. So, let me pull up the slide that goes with that. And let me get the, so you might want to scoot a little bit over, because otherwise you'll be in the view of the video here. And while I'm sure everybody will go like, man, he looks fabulous, they probably want to see the screen too. So, all right. So remember that the reason we don't have a lunar eclipse every time the moon is full, or a solar eclipse every time the moon is new, is because the moon's orbit, the plane of the moon's orbit shown in brown here, is tipped by about 5 degrees to the plane of the Earth's orbit around the sun, shown in blue. Because of that tilt, then usually the moon kind of flies above or below the sun instead of passing right in front of it, or flies above or below Earth's shadow instead of going right into it, so we don't get an eclipse. The line of nodes is the line of intersection between the moon's orbit and the Earth's orbit. That's what the line of nodes is. And for there to be an eclipse then, the condition is that it has to be close enough to true that the line of nodes is pointed at the sun, and it's a new moon or a full moon. Because if, for example, over here, we have a situation where here's the line of nodes, it's not pointed at the sun, then when the moon is new, its shadow is flying underneath the Earth, so to speak. It's missing. And when the moon is full, the moon is flying above Earth's shadow. It's missing Earth's shadow. There's no above or below really, but I'm just, the way the diagram is drawn, I'm calling this below, this above. But when the line of nodes is pointed at the sun, that's when, if the moon is new and the line of nodes is pointed towards the sun, when the moon is at a node, when it is crossing Earth's orbit, in other words, then it'll be almost directly in front of the sun, good enough to get an eclipse. It could be directly in front of the sun, depending on where you are on Earth. Ditto on the backside, if the line of nodes is pointed at the sun, and when the moon is full, then it will be moving through one of its nodes, which means it will be in Earth's orbital plane, and so you'll have a good enough alignment for there to be an eclipse. And so that's the deal with the line of nodes, basically. So follow up, yeah, because people, I always ask, is that good, or you got some more questions about that? So do you have more questions about that, or are you going to ask something else?
No, about that.
About that, ask away.
Think, is that like, what would you mean by the regression of that line?
So that's something else. It's not shown on here. Yeah. Okay. So let's talk about regression of the line of nodes, shall we? All right. So anybody got any more questions just about the idea that the line of nodes has to be pointed towards the sun, and if that happens and you get a new moon, what kind of eclipse do you get? New moon produces what kind of eclipse? Solar, because the sun's getting blotted out. Full moon, lunar eclipse, because the moon is what's getting blotted out. In that case, it's moving into Earth's shadow. Now, if the line of nodes always stay pointed in the same direction, which is the way it looks on this diagram, by that I mean it just stays parallel to itself as the moon goes around the Earth. If it's always pointing off in the same direction and towards distant space, then notice that we would have 2 eclipse seasons. So eclipse seasons are a period of a couple weeks when the alignment is good enough to get eclipses, when the line of nodes is pointing close enough to the sun to get eclipses. There'd be 2 eclipse seasons every year, and they would be how many months apart from one another? 6 months apart. They'd be half the year apart from one another. And eclipse seasons would always be the same 2 months of the year because it always happened in the same parts of Earth's orbit. But in fact, the line of nodes is not quite stationary. The line of nodes undergoes what we call regression. The line of nodes itself is slowly spinning around with a period of some 18 years. I don't remember the exact numbers, 18.62 years or something like that. And that causes eclipse seasons to be separated by more like 5.5 months instead of 6, because the way that the line of nodes is spinning around is the way I'm doing it right here. So in other words, like clockwise in this picture, whereas the moon is going around the sun counterclockwise in this picture. This is the view from above the North Pole of the Earth. So watch what happens. If the line of nodes is slowly spinning like this, then I'm making it actually spin more than it really does. Notice the line of nodes will be back to pointed at the sun earlier than 6 months later. And so the way it works out is that the next eclipse season is about 2 weeks less than 6 months from the prior one, about 5.5 months apart. So what that means is that, in fact, the eclipse seasons move around the calendar. They're in different months and different years. So it's not always the same months that you get eclipses every year. There's 2 months every year that are favorable typically, but the months drift around the calendar from year to year that are favorable for eclipses. Any questions about that? Including what? Could you go over that again? You know, that's always a good question too. Okay. If not, next question. Yeah.
The precession of the equinoxes?
Precession of the equinoxes, yeah. So why, I had a feeling somebody might ask about that, and that's why I brought this, because, you know, we missed 2 classes, one because my eye decided to get infected with bacteria, another one because Mother Nature decided it needed to be too frickin' cold to walk to school one day. And so something had to go. And this is one of the, I just said, okay, I'm just not going to do precession, I'll just let you read about it. But I'll bet when I have a review session, somebody asks me about precession. So I'll take that as my opportunity to talk about it. So this is a model that I can use to represent precession. The idea of precession is that it's only approximately true that Earth's axis of rotation stays pointed in the same direction as we're orbiting the sun. So this picture shows the idea that here is the June solstice. This picture is old enough that it's still called the summer solstice on this picture. Here's the June solstice when the northern hemisphere is tipped towards the sun. Here's the autumnal equinox when neither hemisphere is tipped more towards the sun. Then over here is, the September equinox. And then here's the December solstice when the South Pole is tipped most strongly towards the sun. But notice, Earth's axis of rotation has stayed parallel to itself all the way here. Earth's axis of rotation is just staying parallel to itself. And that's almost true, but it's not exactly true. The Earth's axis of rotation is slowly wobbling around like a top does. The reason is Earth is spinning, and that causes its equator to bulge a little bit. Not nearly as much as it looks like here, because Earth is a fairly rigid body, but the equator bulges. And that means that the sun and the moon pull on that equatorial bulge, and it's as though they're trying to get rid of our tilt, to stand us up instead of having us be tilted. So I'm going to use this model here where it's Earth's gravity that's really doing it, when for the actual Earth it's the sun and the moon. So you can't tell just by looking at me, but there's this big iron yoke under here. So this is actually quite heavy, as a matter of fact. And I'm going to balance it on this pivot point. And it's this big iron yoke in here puts the center of gravity over the pivot point, with the result that this thing acts like a pendulum, basically. In other words, if I swing it like this and let go, it does that. It just wobbles back and forth along a straight line. Earth's gravitational torque, we say, is trying to untip it, but then it overshoots and goes the other way. But watch what happens when I spin it before I let go of it. So I'm going to make it act like a top, or a gyroscope as it's called. If I spin it and let go, watch what it does. And what I want you to really concentrate is not the whoa, 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 but just the overall, the way it's going like that. In other words, precession means that Earth's axis of rotation is slowly wobbling around like this, tracing out a cone. So if right now, Earth's axis of rotation, represented by this guy right here, if right now that's pointing to the star Polaris, well, the precession cycle is very slow. It takes about 26,000 years to go all the way around. So it's very gradual. In any 1 year, our axis of rotation hardly moves at all. Wait long enough, though, and it moves a lot. So our axis of rotation just happens to be pointing at Polaris right now, almost perfectly. Wait a few thousand years, and it's not pointing at Polaris anymore. Polaris won't always be the North Star. It just happens to be the North Star now because our axis of rotation is nearly pointed at it. Here is a representation from your book of that idea. Here's the Earth's axis of rotation now, points toward Polaris. Half a precession cycle later, about 13,000 years from now, it'll be pointing closer to the star Vega, although Vega won't be nearly as good a pole star as Polaris is now. Here's another representation. This is the path that the North Celestial Pole follows amongst the stars due to precession. So here was AD 1. Was Polaris a very good pole star back in AD 1? Not so great. But now, Polaris is only about a degree from the North Celestial Pole, so it's quite close to it. But as time goes on, here's AD 8000. Polaris is no longer even close to being the pole star. At the time the pyramids were built, around 2500 BC, Thuban, maybe it was 3500, I forget now. But anyway, Thuban was the North Star back then. So the ancient Egyptians used a different pole star than we do, and it's because of precession, is what it comes down to. Another reason that astrology is bullcrap is that for most people, say you're a Sagittarius, the sun probably was not in Sagittarius on your birthday, and that's because of precession. Because if I think of this as being the plane of Earth's orbit, then this would represent the ecliptic. Here is Earth's equator, which we can also, because we projected on the celestial sphere, think of the celestial equator. If the direction of Earth's axis of rotation is moving around, so is the intersection between the ecliptic and the celestial equator. Or in other words, the constellations that the sun is in at different times of the year changes over time. Right now, the spring equinox is in Pisces, but it used to be in Aries, which is why the name for it is the first point of Aries. Right now, the December solstice, December solstice is in Sagittarius. It used to be in Capricornus, which is why that southern tropical limit of the tropics on the Earth is called the Tropic of Capricorn. We would name it the Tropic of Sagittarius if we named it today, but it's named after where the equinoxes and solstices were about 2,000 years ago. And precession has caused the constellations the sun is in to no longer agree with the so-called sun signs, because the sun signs are based on where the sun would have been like 2,000 years ago at that time of year. When precession of the equinoxes was discovered, astrologers had to choose whether they would update with the times or just always keep it the same as it was at an arbitrary point a couple thousand years ago when the system was invented. And they chose to just keep it like it was when the system was invented. So most people are surprised when they discover that the sun is almost certainly not in their constellation on their birthday, that their sign is named after. Anyway, that's my little rant. Okay, so any questions about that? Okay. Next question. Yes?
Can we work through a problem or two of the moon phase wheel?
Well, the moon phase wheel, okay? Give me a problem and I'll work through it.
Oh boy.
Just like if you have the exercises with you, just give me one of them, right? Give me one of the ones that I was asking you to do, and I'll be happy to work through it here. So how about, let's start with that one. Number 2, what's the second one on there? Somebody have it with you? So of the exercises, I say, here's some exercises to do. What's number 2? And actually, I'll just live with it. I'll get my hands dry with chalk dust. Yeah, so what's the second?
Example 2 is it's 3 p.m. The phase of the moon is first quarter. In what direction must you face the sun?
Okay, all right, so it's 3 p.m. Moon phase equals first quarter. And what direction then is the moon? Okay, this is our task. So, first thing, of course, draw the moon phase wheel. All right, so what's up top? What direction?
Noon.
Yeah, noon, and then what about compass direction?
South.
South, because that's supposed to represent high in the sky to the south. At our latitude, the sun and the moon, when they're high in the sky, you're facing south to see them. So we put that up top to represent that. So on the bottom, north, and the time, midnight. Remember that the times only apply to where the sun is, not where the moon is. Because we tell time by the sun. Then over here on the left, direction, east, because we're facing south. It's like, hi everybody, I'm facing south. So east is on my left, west is on my right. And for simplicity, we say the sun rises at 6 a.m. and sets at 6 p.m. Of course it varies, but good enough for our purposes here. Okay, it's 3 p.m. If you're told what time it is, that's code for, I just told you where to draw the sun, because we tell time by the sun. So the sun must be halfway between noon and 6 p.m. So the fact that it's 3 p.m. tells me draw the sun at the 3 p.m. position like that. And then I put little rays on it so I don't confuse it with the moon. And then I make a lollipop. The observer's in the center. There's my tasty sun lollipop. Draw it like a stick to the center there. So what direction is the sun at that time? What would you call the direction of the sun? Southwest, because it's in between south and west. All right? Now the moon phase is telling you the angle between the sun and the moon and which direction to go to get from the sun to the moon. So you want to burn this into your head, okay? That if you remember these things, you're pretty much golden. So, first of all, is first quarter, is that a waxing phase or is that a waning phase? It's waxing, because first quarter is when it's going to go to gibbous and then full. So that's a waxing phase. Waxing. Angle from sun to moon is on the wheel counterclockwise. You got to go counterclockwise to get from the sun to the moon. You got to go this way, because if you're above the horizon, that would be eastwards, towards the eastern horizon. So waxing phases are east of the sun because the moon is orbiting us from west to east as it orbits us. Waning angle from sun to moon is, what am I going to say? Clockwise. Yeah, clockwise. Because remember we said that waning phases were west of the sun. If the sun's above the horizon to get to the moon, if you went clockwise, you'd be going to the western horizon. The moon would be west of the sun. We had our mnemonic to remember that waning phases are west of the sun. We said Cowboy Wayne lives out west. Let's add to it. To remember that on the moon phase wheel, that means you go clockwise. Cowboy Wayne lives out west where he runs a clock shop. Besides, you can come up with your own, but that's what I would suggest. Okay? So Cowboy Wayne lives out west where he owns a clock shop, so it must be waning phases. You go clockwise on the wheel. So waxing or waning tells you which way to go from the sun to the moon. And then the next piece is, you got to remember how the angles work. So, what's the angle between the sun and the moon, essentially, if the moon is new? Zero, because basically if I'm pointing at the sun, I'm also pointing at the new moon, because it's in between us and the sun. It's not a perfect alignment, unless we got an eclipse, but whatever, good enough. So new, 0 degrees. Okay? And here, I'm not going to bother distinguishing between waxing or waning. I'm just going to say crescent, because the waxing or waning figures out the direction, but the angle doesn't matter. The angle doesn't matter whether it's waxing or waning. But I'm going to skip crescent and go to quarter. And then there will be gibbous and then full. Quarter. What's the angle from the sun to the moon at the quarter phases? 90 degrees. Yep. So 90 degrees at the quarter phases. I don't know if the people at home can see this. If not, listen carefully, people at home. 90 degrees. Actually, I'm kind of curious. Can the people at home see that? The people at home being the people that are going to watch it on YouTube later. Let's let the people at home see it. We like them too. There you go, people at home. Thank you, Dr. Herman. Oh, you're welcome. Okay, so. And then, what about full? 180, opposite sides of the sky. Okay, so for crescent, it's in between 0 and 90. Often we'll split the difference, not always, but often it'll be like, if it's halfway, it'd be 45. But in general, it's 0 degrees is less than the angle theta is less than 90 degrees. Or in other words, what do you call that? A geometer would call that what kind of angle? Acute, yeah, it's a cute little angle. For gibbous phases, it's going to be between 90 and 180. So 90 degrees is less than the angle, is less than 180 degrees. What do you call that? Obtuse. So if it's an obtuse angle, it's a gibbous phase. If you remember those things, that's most of the battle for doing this. So the time told us where to draw the sun. The phase of the moon tells us where to draw the moon. It's first quarter. What's the angle? 90 degrees. Now, which way do I go from the sun? It's a waxing phase, so I go waxing is counterclockwise. So I go this way 90 degrees, like so, 90 degrees that way, and that tells me where to draw the moon. So what direction is the moon at that time? Southeast. Southeast, yeah, bingo. Southeast, because there it is, in between south and east. So it's very systematic. This is something where once you get it, but you gotta get it. Okay, that's an example. Want to do another one?
Yeah.
Okay, let's do another one. So let's do, that was number 2, right? Let's do number 5. Let's do 1, 2, 3, 4. Yeah, let's do number 5, let's say. Can I erase this? All right. Of course, these days the quickest way to take notes is, all right, what's number 5 say?
At what time is the last quarter moon on the meridian in the south?
Okay, at what time? At what time is the last quarter moon, also known as third quarter moon, on the meridian in the south? In other words, high in the sky to the south. Okay, so this time we're being asked what time. We tell time by the sun. So this time the key is that we're going to draw the moon first because we were told where the moon is. It's on the meridian in the south. And then we're going to use the phase of the moon to figure out where the sun is. And then we'll read off the time from where the sun is in the sky. So the first example we did, we were told what time it is. That told us where to draw the sun. If you're asked what time is it, you have to figure out where to draw the sun in order to read off what the time is. So I'll draw myself a fresh new crappy moon phase wheel here. Whoops. South, noon, west, 6 p.m., north, midnight, and east, 6 a.m. The moon is on the meridian in the south. Tell me when to stop and draw the moon. Stop, yep. So the moon is on the meridian in the south. Draw the moon lollipop to the center. Now, you got to be careful here. We drew the moon first. The waxing and waning business tells you the direction from the sun to the moon. So in other words, here we got to be careful. Don't go from the moon to the sun these directions. You go from the sun to the moon these directions. So, the moon is third quarter. Is that a waxing or a waning phase? That's waning. So, sun to moon is what direction? Clockwise, right. So, sun to moon has to be clockwise. All right. And furthermore, it's a quarter phase, 90 degrees, okay? So one way to do it would be like, it's 90 degrees, so maybe the sun is here, maybe the sun is here. The right one is the one where going from the sun to the moon is the right direction, clockwise. So if I put the sun right here, would I be going clockwise from the sun to the moon? No, so that can't be the right one. It must be that the sun is right there, because then I'll be going the correct direction of clockwise 90 degrees to get to the moon from the sun. So what time is it? 6 a.m., which you could also just say it's sunrise. Yes, sunrise is in the east. So yeah, sunrise. So if the moon's third quarter, you got it sunrise, you'll see it high in your sky to the south. That would be the idea there. It's up to you if we do another one or not. Not anymore, huh? Okay, so, but take what I just did, and if you haven't done those exercises, do them, practice, because there's a number of them on the exam, guaranteed. So you don't want to lose those points, because if you know what you're doing, you'll get those points. I want you to get those points. Students sometimes don't imagine that professors get nervous before exams. We do, because we don't want to feel like we suck, because I don't want to grade the exam and like, God, I didn't reach them at all. That feels terrible. So I want you to do well. Which doesn't mean I just make it easy or whatever, but in other words, I want you to do well on an exam which would show that you knew what you were doing. I will say, though, that it is true that when it comes to exams, it is better to give than to receive. I will admit that. Okay, next. Yeah.
So this is really basic, but the meridian,
Yeah.
what, like, your meridian is, so in this case.
So unfortunately, yeah, so one problem is the word meridian is used in a number of ways, but the one we're using it here, okay? On the celestial globe, this is the meridian. This thing right here represents the meridian. Notice it intersects the horizon north and south and goes through the zenith, the point overhead. So if I were to draw my meridian, what I do is I point, and again, who knows what I do? I point due north, I point due south, and then I go like this, and I'm tracing out my meridian. So my meridian goes from my due north on the horizon, straight over my head, down to due south on the horizon.
So then how does that compare to your zenith, if that's right overhead of whatever?
So careful, because the claim on the moon phase wheel, it's just a representation. It's a two-dimensional representation of a three-dimensional, really, situation. So I'm not claiming here that the moon is over my head when I draw it right here. I'm merely claiming that it's at its highest point of the night when I'm drawing it right there. Because I'm going to turn things around. Suppose now this is south, okay? So south, zenith, north. Moon rises in the east, but at our latitude, the moon never goes over our head, but it does climb into the southern sky, and it gets to its highest point above the horizon when it's on the meridian, and after that, it starts to sink back towards the western horizon.
So the meridian, if it's the highest point, it's just the highest point. Or
It's
the
just-
zenith is always straight 90.
The zenith is always straight overhead, but depending on a star's declination in your latitude, it'll be highest in the sky when it crosses the meridian at its high point, but it may not be very high in the sky. If it's like a far southern star for us, they just go, whoop, hi there, and then they go back down again. If it's a far northern star, it'll cross the meridian and not even be at the zenith, it's to the north of the zenith. It just depends on where it is in the sky. But any star on here, like here's Deneb, I will follow Deneb across the sky. Notice my finger is getting further and further from the horizon here until it gets to the meridian. And then as soon as it crosses the meridian, it's getting closer and closer to the horizon again. So the meridian, that circle from north to south that goes over your head, when things touch that circle, they're as high above the horizon as they're going to get. They're rising until they get to the meridian. They're setting after they cross the meridian and go to the other side of it. Yes.
Can we go over the umbra and pre? Oh,
The umbra and penumbra.
yeah.
Sure, parts of a shadow, yeah. So remember that, which part's darker, the umbra or the penumbra? Umbra is, yeah. Okay? So here's the figure from your book that illustrates that idea. It's using the Earth here, but the moon also has an umbra and penumbra. So the umbra is like the ice cream cone that has the Earth or the moon as the delicious ice cream at the top. The penumbra is the lighter part of the shadow. And remember that the distinction between them is that if you are floating around inside the umbra, the sun is completely blocked out from your view. In other words, any line of sight that would get to the sun passes through the Earth first if I'm inside the umbra. There's no clear line of sight to the sun if I'm inside the umbra. But if I'm inside the penumbra, some clear lines of sight to the sun exist, so I do partly see the sun, but other lines of sight to the sun are blocked by the Earth or the moon, depending on who's casting the shadow. So the difference between the umbra and the penumbra is that in the umbra, the view of the sun is completely blocked. In the penumbra, the view of the sun is only partly blocked, and that's why the umbra is darker, because the sun is completely blocked inside the umbra, whereas in the penumbra, the sun is only partly blocked, and so you only partly reduce the amount of light that you're getting compared to not having any blocking whatsoever. So if we are on Earth and there's an eclipse of the sun, and do I even have that somewhere there? Somehow I skipped that. But anyway, if we are on Earth, there's an eclipse of the sun. Maybe I do have it further on. Yeah, there we go. We're on Earth. There's an eclipse of the sun, and where we are at that moment is in the moon's penumbra. What kind of eclipse are we seeing? It's solar, but in other words, is it total or partial? Partial. If you're in the penumbra, the sun is only partly blocked by the moon, so you're seeing a partial phase of the eclipse. To see total eclipse, you have to be along the line of totality, which is where the sun's umbra sweeps across the Earth. Down there I got it for an annular eclipse, but up here, they have it for up here, if you are on the part of the ground where the moon's umbral tip sweeps past you, then while you're in the umbra, the sun is completely blocked and you're seeing a total eclipse. On the other hand, if the moon is too far away so that it doesn't look as big as the sun does, then the best you can do is an annular eclipse where the moon has a ring around it, a ring of sun around it, but the moon is too far away to be big